Hello everyone, Professor Sura here, and today we'll be discussing some titration calculations. So these can get overwhelming pretty quickly unless you have a good sense of where you're starting and where you're going and what you're working with. So it's always good to label your units very carefully, take your time, and just ask yourself, what am I looking at any given moment? So we'll go through these examples and that should help. My pointer going on. So on the screen here are two different titration examples. We're going to go through all of these. The major difference, if you read through these, they look very, very similar. The major difference is the first one uses hydrochloric acid and the second one uses acetic acid. So hydrochloric acid is a strong acid and acetic acid is a weak acid. Both of these are being titrated with KOH, potassium hydroxide, which is a strong base. So that's the different types of titrations you can encounter. So you either have a strong acid and a strong base, a weak acid and a strong base, or a weak base and a strong acid, which we're not going to do in this video, but it's definitely something you can encounter. You wouldn't normally titrate a weak acid with a weak base. It just makes life a lot more complicated. You definitely have reactions where weak acids can react with weak bases, but that's not how you would design an experiment used to determine the concentration. So titrations are generally used to measure the concentration of an unknown. These examples right here are to show you what you should expect when you know the molarities and the volumes, right? So this is more of a theoretical exercise. And then if you went to lab, you could test it using a pH probe and stuff like that. So we can do lots of calculations with these titrations, which is why it's a really good example of your knowledge so far through chemistry. Okay. So let's just dive into, we'll do this one at a time. The very first one asks you to write the balanced chemical equation right here. So it's always good to ask yourself what's going on in this reaction or in my flask or whatever. So let's start with that. So you have hydrochloric acid reacting with potassium hydroxide, one-way direction because it's a strong acid and a strong base, and we're going to always form a salt, so the potassium chloride from your cation here and your anion there, and then water. And that's generally what a acid-base reaction or a neutralization reaction will form, a salt and water. So this is your balanced chemical equation. You can include all the phases if you want. It's good bookkeeping. Aqueous, 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 liquid. It's how we can actually say we got a reaction because we form a liquid or solid. And so the very first question then, after you write your balanced chemical equation, asks you, what is the pH of this solution before this reaction even occurs, right? So we haven't added any KOH yet. I just have a beaker containing hydrochloric acid. And it's 0.2 molar. You have a strong acid, so if I had 1 mole of HCl, I would get 1 mole of KCl3. Actually, let's draw this out. So before you add the KOH, it's just HCl sitting in water. So the question doesn't ask you to draw this, but you should always kind of ask yourself, what is my reactant doing? And this is what makes it an acid to begin with. It donates its proton to the water. This is your acid. This is your base in this instance. You end up with your counterion over here. But this happens in a 1-to-1 ratio, 100% dissociation, or like 99.99%, whatever they say. So if I have 1 mole of HCl, I get 1 mole of hydronium. If I have 0.2 molar HCl, it directly converts to 0.2 molar hydronium. This is the beauty of the strong acid. So you always want to be cognizant of what you're working with. So this is the name of the game for your pH calculations. We need to get the hydronium or the hydroxide, depending on what angle we're coming from. So it doesn't get much easier than this. When you have a strong acid, the concentrations are the same. Because this is really what's in the flask, right? There's none of this hanging around. It's already dissociated and cut into half, and the chloride's off doing its own thing. So take the negative log of the H3O plus concentration, or the brackets means molarity, and that is your pH. So the negative log of 0.2 ends up being 0.69. Something like that, right? So a very low pH because we have a strong acid of a reasonable concentration. You can definitely go into negative pHs, and you can have pHs greater than 14. The scale you're most familiar with, like 0 through 14, is more of the stuff you encounter in real life, like biological or in nature. You don't necessarily see like concentrated HCl hanging out anywhere or concentrated sodium hydroxide. So that's kind of why that scale is what we use in general. Okay, so the next question then asks what happens after we add a little bit of the KOH. So let me write that reaction again here. So we have H, because this is like the rest of the actual titration. H3O plus and KCl. Okay, so after we add 5 milliliters of KOH, remember all of these balanced chemical reactions are showing us mole to mole ratios. So when in doubt, convert to moles. So if you have 5 mils of a KOH solution, right, it's not just pure potassium hydroxide, it's a diluted solution. We can get the moles from that by going from milliliters to liters, and then the molarity of 0.200 moles KOH for every 1 liter. You can calculate that out, and you end up with 0.001 moles of the KOH added. This is what we delivered using the burette into our beaker. And these are going to react in a 1-to-1 ratio with the acid, right? That's what this balanced chemical equation is telling you. So if I added 1 mole, I would react with 1 mole of HCl. If I had 0.001 moles of KOH, I react with 0.001 moles of HCl because it's a 1-to-1 ratio. So you can show that. I'll show it once the long way, and the rest we can do it. Mole of KOH. And I know that for every 1 mole of KOH, I react with 1 mole of HCl. Right, so 1-to-1 ratio, be mindful of this step. Don't just always assume that the moles of base added is equal to the moles of acid reacted if you have a different ratio from your balanced chemical equation. So it's why it's always good to do it the long way and understand the concepts. HCl reacted. Okay, and how much HCl did I have to start with? I had 10 mils. And you convert that to moles as well. It's all about the mole ratio. Moles of HCl for every 1 liter of solution. Excuse me. That ends up being 0.002 moles of HCl initially or originally or to start, whatever you want to call it. Okay, so I have this much to start, and then I react this much. You can subtract them. And notice my units are matched up, right? Moles of HCl, moles of HCl. So that's why it's really good to keep track of all your units. And notice everything I have here is labeled because it's really easy to get lost. So what you're going to do is take the 0.002 moles of HCl initially, minus the 0.001 moles reacted, because that's what actually physically happened when we added the KOH. And we're left with 0.001 mole of HCl remaining in our flask. So let's calculate the pH of that. If I have 0.001 liters of HCl, moles of HCl left, what's in my flask? Remember, I started with 10 milliliters and then I added 5 more milliliters of solution, mostly water. So my total volume is now 15 milliliters, which we can convert to liters by dividing by 1,000. So I'm going to do that one step there. That's the 15 mils that's present in the flask. If you have questions on where that came from, please let me know. So my new molarity is 0.001 divided by 0.015. On my notes, 0.00 or 0.06667 molar HCl. And remember, that's the same as the molarity of the H plus or the H3O plus. So we can directly take the negative log of that. Because it's a strong acid, you can't always do this. So just keep track of what's going on. 0.667, couple sixes. It's a bunch of sixes repeating, so just keep track of that. And you get 1.17 molar pH. No units on the pH. pH equals 1.17. I'm used to writing molar after everything. And that makes sense. The pH went up. It got more basic as we added more base. So that's a logical value for that. Okay, the next question asks what happens when you add 10 milliliters of the base. And what happens here is when you convert this all the way to moles, you end up with the same amount of acid we had originally. So the amount of KOH added is equal to the amount of acid that was present. So they completely react at a 1-to-1 ratio and they're gone. So then what do I have left in my flask? If you look at the balanced chemical reaction, you just have KCl and water. And then potassium chloride, KCl, is a neutral salt. You know this because it has the cation of a strong base and the anion of a strong acid. So these are not going to behave like an acid or a base. It's a neutral salt. You can have neutral, acidic, and basic salts. And we'll talk about that a little bit more later. But the whole point here is that the only thing in my flask is water, which is an amphoteric or amphiprotic species, which means it reacts as both an acid and a base and forms your hydronium and your hydroxide in very, very small concentrations. This is a special equilibrium called the autoionization of water. There's a Kw associated with that. It's the equilibrium constant specifically for water. It behaves exactly like every other K you've seen before for equilibrium. And these are both liquids, aqueous. So we can write an equilibrium expression where the Kw is equal to the concentration of H3O plus and the concentration of OH minus. And we leave off the reactants because they're liquids. This is all a review from the equilibrium chapter. So you can solve for the concentration of H3O plus here because you can just say they're both equal to X because they're a 1-to-1 ratio. So the Kw is equal to X squared. Kw is a constant at room temperature, so because it's temperature dependent, at 25 degrees Celsius. Kw is 1.00 times 10 to the negative 14 equal to X squared. If you take the square root of that, you get X equal to 1.00 times 10 to the negative 7, which is my H3O plus concentration, and my OH minus, depending on what you want to do next. But we want the pH. So we'll go next slide. pH is equal to the negative log of the H3O plus concentration, which is the negative log of the 1.00 times 10 to the negative 7. And that gives you pH equal to 7. This is why 7 is neutral, because it's the pH of water when it's by itself, reacting with itself. There's always a little bit of hydronium and always a little bit of hydroxide present in any aqueous solution. Okay, and this is your equilibrium, your equivalence point, the moles of acid. Originally were completely reactive with the moles of base added. So this is where, the equivalence point, or if you added another drop when you're physically doing the titration, you would hit your indicator. Your phenolphthalein is usually used. So a very important point in the titration. The next question asks if you added 15 mils of KOH. So let's look at that. Converting it to liters, and then using the molarity to convert it to moles. That ends up being 0.003 moles of KOH. That's the KOH added. And remember, we originally had 0.002 moles of HCl. So we're going to add more KOH than we had acid to react. So it's going to completely react, and I will quench all of my acid, and then I'll have some leftover KOH. Right? If I add 0.003, it reacts with 0.002. I have 0.001 molar, or moles of rather, KOH remaining. And then you can convert this to a molarity divided by the total volume, which was 15 mils of KOH added, and then the original 10. So it's 25 mils or 0.025 liters. When you calculate this concentration, you get 0.04. And that's the molarity of the KOH. I like to just take this from here and calculate the POH because it's already in my calculator. So it's the negative log of 0.4. So the POH ends up being 0.397. And then the pH and the POH are related. POH plus the pH is equal to 14. not negative 14, sorry, 14. So you can quickly calculate the pH from the pOH, just subtract it from 14. So 14 minus the 0.397 gives me a pH equal to 13.6, which makes sense for a solution of KOH, because what do I actually have in my flask? It's just potassium hydroxide, a strong base, so I should have a really high pH. It makes a lot of sense, right? So we went from a low pH, because it was an acidic solution of HCl. We completely neutralized it all and then reacted a bit a bit more. This is why you see your titration curves look kind of like this. If the pH is on the left and your volume's right here, you start low and then inflect up like that, and that's your equivalence point. This is your high pH when you have excess base. This is when you have just the acid present. So that's a good looking example of a titration curve. Okay, so the strong acid, strong base calculations are challenging on their own, and you should definitely practice this. I would get this down pretty good before moving on to a weak acid or a weak base titration, because it's a bit more of the same and then some other new stuff, but all of this you've seen before. The new thing we're really doing is just adding pH to all our calculations. Okay, for the weak acid, we have acetic acid reacting with the same base. There's equilibrium going on. Actually, no, this is a one-way arrow because of the strong base. We don't have an equilibrium yet. So this will completely react. This is where I got hung up a lot as a student, because I'm like, oh, it's a weak acid, it's only going to react a little bit. It's like, no, with the strong base present, it's completely pulling off that proton. So you get your acetate here, and the K from the base kind of hanging out. And then we end up with water, like we always do, salt and water. So it's potassium acetate as your salt, and water is water. All right, so there's your balanced chemical equation. So the question asks, what is the pH before we add any of the KOH? So we just have a flask containing CH3OOH. That is your acetic acid, and it is going to behave like an acid in the presence of water. Here's where equilibrium error comes into play. We get the acetate again, and our hydronium. This is why it's a weak acid. But it's weak. It has a Ka value here. That's how you know it's a weak acid. The Ka value of 1.75 times 10 to the negative 5 is a constant at 25 degrees Celsius. So before we add any of the KOH, all I have is a weak acid dissociating into its conjugate base, and the base turning into its conjugate acid. This is the review from the equilibrium chapter. We can just set up an ice chart. You can always calculate an equilibrium concentration if you know the starting concentration of a weak acid or a weak base or anything that's dissociating with its K value. So this is 0.200 molar. We don't include liquids in our calculations, and this is going to be 0 to start and 0 to start. This is going to go down by x. This is, again, we don't care about that one. It's going to go up by x, up by x. It's a positive sign, x, negative x. So at equilibrium, I'll have my original molarity minus x, and then I'll have these guys, whatever amount dissociates, that's what they turn into. So you can quickly set up your equilibrium expression where you have the Ka equal to the products raised to their respective powers times each other. They're both raised to 1, which we don't include. My hydronium divided by the reactants. Okay, if you are having trouble with ice charts, refer to the previous videos, but also let me know. I'd be happy to work through these with you. You should definitely know how to do ice charts by now. So plug in your equilibrium values. We have the Ka of 1.75 times 10 to the negative 5 equal to x times x divided by 0.200 minus x. Right, all of this came from this row here. All right, so this is equal to x squared over 0.200 minus x. And we can do the x's small approximation where we just get rid of this, because our concentration is a large enough difference between the Ka value. And you should always be able to do this for the titrations in this chapter. On my exams, the homework might be different. So we end up with just x squared over 0.2. I'm going to go on to the next slide and clean this up a little bit. So what you've boiled it down to is 1.75 times 10 to the negative 5 equals x squared over 0.2. So solve for x. You end up with 3.5 times 10 to the negative 6 is equal to x squared. And then take the square root of the left side. I usually raise it to the 1/2. That's how I do it in my calculator, but that's fine. So you end up with x equal to 0.00187. And what is the x in this case? Go back and look at your ice chart if you need to, but this is the hydronium concentration. So we're in good shape to go from here. So we can now take the negative log of this to get our initial pH. Equals the pH equals 2.728. Right, which makes sense. It's a 0.2 molar solution of a weak acid. The pH is going to be less acidic. So if you look back at your HCl, our strong acid titration, the pH was much lower than this because it's more acidic. So we're kind of just proving that this is a weaker acid as far as the concentration of hydronium. All right. So the next question asks, it's the same volume amounts. So all the moles of base added are the same as the first example. I'll still go through a little bit, but just so you kind of see what we're not changing anything about the base. So if we have that 5 mils of KOH, we can convert it to liters and then convert to moles. It's all about the moles. Right, so we're still getting the 0.001 moles of KOH added. And this is still equal to the moles of acid reacted because of the strong base nature. It's going to react with any available acid. So this is also equal to the moles of the acid reacted. So if you look at the initial amount of your weak acid, we have 10 mils of CH3, COOH, convert it to liters like we like to do, and then convert to moles. We get 0.002 moles of CH3. Initially, before we add anything, right, this is the same mole amount as the hydrochloric acid also, right? It's still the same concentration, just how much of that is actually available as an acid is the difference, but just kind of tying it back to that. So we still add 0.001 moles of the base, and it's going to react with 0.001 moles of the acid. I'm going to be left with 0.001 moles of CH3 COOH remaining. The thing to note here, let me go back a slide, is that when we add the KOH, it reacts with the weak acid, and the new part for this is that we generate a conjugate base. So let's look at that salt, potassium acetate, because we also generate 0.001 moles of CH3 COO minus plus produced or generated, or however you want, it's the product. And again, this number came from the moles of acid added. The moles of acid added before the equivalence point is always going to end up being the moles of your conjugate base created. So this is a special scenario where this is what's in my beaker right now. I have an acid and its conjugate base, or base and its conjugate acid. This is your buffer solution. So every point in the titration before the equivalence point is going to be treated like a buffer with a weak acid, strong base, or even a weak base, strong acid. So when you have a buffer, you pull out your good friend, the Henderson-Hasselbalch equation, plus the log of the concentration of the conjugate base over the concentration of the weak acid. This is what I like to use. Students I see learn about like as base over acid, and that's still true in this case, but you need to use the conjugate base from these should be related to each other, right? I see a lot of students plug in the OH minus concentration here. That's not what you're doing. It's the acid in its conjugate base or the base in its conjugate acid. That's how you want it. They're tied together. That's the whole point. So we talk about buffers in another video, but for now we're just doing pH calculations. So you take the pH equal to the pKa is the negative log of the Ka, which is 1.75 times 10 to -5 plus the log of, in this case, it's 0.01 moles divided by 0.001 moles. So these end up dividing out to 1. You don't need to use, I know this says molarity. You can use moles because if you want to convert these to molarity, you can. You divide by, what do we add? 5 mils of KOH. So we have 15 mils total. You can do 0.015 liters divided by 0.15 liters. You're going to get the same answer. I'll let you practice that on your own. So you're welcome to do it and follow the rules, or you can take a shortcut and save yourself a little bit of time. So the pH is equal to the negative log of the Ka is 4.76. which is your pK. And then when you have 0.001 divided by 0.001, that goes to 1, and the log of 1 is 0. So we immediately get our pH. It's a nice, easy one. So let's keep track of that. So this is your pH after about 5 mils have been added. The next question asks what happens when we add 10 mils of KOH. Convert to liters, like we like to do. So this gives me 0.002 moles KOH added, which is the same as the acid reacted. And I started with 0.002 moles of acid to begin with, right? So I had 0.002 moles of CH3COOH before I added any KOH. And then I added enough to react with 0.002 moles CH3COOH reacted right from here. It's a 1-to-1 ratio. So I have none left over. I've completely neutralized or quenched or reacted all of my acetic acid. What is in my beaker now? All of these moles of acetic acid turned into moles of your potassium acetate. So I have a beaker of potassium and acetate. This is different than what we had at the equivalence point with the strong acid, strong base. At the strong acid, strong base, we just had potassium chloride, which was a neutral salt. This is a basic salt because you have the cation of a strong base and the conjugate base or the anion of a weak acid. So that's going to behave like a base in water, right? If I draw the equation, react it with water, because that's what's in my beaker right now, right? This is this guy hanging around. I end up forming a little bit more of the proton-on form on the acid, and then hydroxide. That's what makes this a weak base, because it generates a little bit of hydroxide in water. And from here, we just do another ice chart. Because you have a weak base floating around by itself. Remember, these molecules don't know they're being titrated. They're just living their lives. All right, so go through the ice chart again. Let's talk about that. I'll do the next slide. For the ice chart, you need the Kb in this case. Let me go back one slide, actually. This, as the forward reaction, is a Kb for the equilibrium of the base. It's behaving like a base. This Kb matches up to that. So the way we do that is that the Ka times the Kb is equal to the Kw. So you can always calculate a Kb from a Ka or a Ka from a Kb. The Kb in this case is Kw divided by Ka, which is 1.00 times 10 to the negative 14 divided by 1.75 times 10 to the negative 5 equals your Kb of 5.714 times 10 to the negative 10. Right, and then you go through and set up your ice chart again. I'll let you practice that on your own. They all, for these weak acid, weak bases that are monoprotic, it's always going to be your K equal to x squared over whatever your concentration is. And then with the x is small, you get rid of the x that you would be subtracting there. So this is what it always is. It's basically the only thing you're really changing is you're plugging in a different constant. Here's our Kb. And if I give you a different concentration, but you're always going to end up here. So practice the ice chart on your own, but like this is kind of like your template for your weak acid or weak base calculation. Okay, from here we can calculate this is equal to 5.714 10 to the negative 10. You end up with x equal to 1. Yeah, let me make sure I got my notes right. 1.06 9 times 10 to the negative 5. And remember what x is in this case. Go back a slide, right? It's my OH minus concentration. These are my x's in this case. We'll leave this guy out again. Okay, so that's the OH minus concentration. I also like to go right to POH from here, take the negative log of this value, and you end up with the POH, which is equal to 4.97, and then the pH, after subtracting from 14, is equal to, right, the POH plus the pH is equal to 14. So you can subtract this from 14 and get a pH value of 9.03, which makes sense because we have a slightly basic solution due to the salt, the basic salt from the acetate, so 9.03. Okay. The next question is identical to the question from the strong acid, strong base, because what happened was we added 15 mils of KOH, convert this to moles like we always do. And you end up with a 0.003 moles of KOH added, and it's going to react with all the acid present. I had 0.002 moles of my weak acid. All of that gets reacted. I'm left with 0.001 moles of just KOH by itself in a beaker of 25 mils of acid, because I had 10 to start with, and I added 50, or 25 mils of water rather. I had 10 mils to start, and I added 15, so I got 25 milliliters, or 0.025 liters. This is the same concentration that we had after the first titration, because again, the molecules don't know what you're doing. We neutralized all of the weak acid. We're just left with this molarity of KOH again. That's what's in the beaker. And you can go back and look at the previous slide or practice it on your own, but you end up with a pH equal to 13.6. Because it's just excess base. At the end of both these titrations, all I had was a bunch of leftover base, a strong base. Okay, so those are what you're going to encounter. The only one we didn't cover is a weak base, strong acid titration. It's the exact same thing, just backwards. You start with a high pH and you go to a lower one. But I highly suggest practicing that. There's some really good examples in the homework as well. Please let me know if you're having trouble with any of this, or if you notice any errors in my math, or you have any questions. I will be glad to work on this with you for as long as you want. So just contact me anytime you can. Thank you for your time. Please enjoy the rest of your day.